So today's lesson will be on gravimetric analysis of a mixture. Gravimetric analysis is just the idea that we use weighing or some kind of weight measurement to determine the composition of a mixture. If you look at the word gravimetric, so metric means to measure or to, so that suffix usually applies to measuring things. And gravi is like gravity, so gravity is related to weight. So if you think of the word gravimetric, you think of weight measurement. That's how we can remember that term. This picture here is a centrifuge, and a centrifuge is used in the medical industry as well as many other biomedical industry to separate mixtures so that we can weigh the components of the mixture and figure out what its composition is. So that's just one way we can gravimetrically analyze a particular substance. But in today's lesson, we want to apply gravimetric analysis to a mixture of sand, water, and salt. Imagine that you just went to the beach. You just took a beaker and scooped just a bit of the sand out of the beach. Well, it would be some kind of mixture of sand, water, and salt. And we're going to use gravimetric analysis to figure out how much of each component is in this mixture. The supplied sample tube, which we'll get, contains a mixture of sand, salt, and some water. So typical of what you would see at a beach. There's some dry sand. It'll have salt in it because the seawater would have washed onto it. And there might still be a little bit of water on there. So it'll be sand, salt, and maybe a little bit of water because it's a bit damp. And then we're going to separate them by using the chemical properties of each particular part. And then we can understand how much of each particular component we'll have. So the first thing to do is we're going to have to measure a lot of things, gravimetric analysis. So we need to make sure we keep track of what we're weighing, okay? Otherwise, it'll just become very difficult to analyze the system. So first, we're going to weigh the tube, which has the salt mixture, or the sand, salt, water mixture. And then we're going to record the mass. And that's going to be M1. Okay, so the first mass that we measure is going to be the mass of the whole thing, which makes sense. So just keep M1 in mind, and then we'll, as we go on, write down what each of these masses is. So using a wash bottle and a stirring rod, we transfer the contents of the tube to some filter paper. So what we want to do here is we had a tube full of sand, salt, and water, and then we poured it onto into a filter paper. See that in the top of each of the filter funnels, we see some white paper looking stuff. That's the filter paper. Why we want to do that is because obviously we can filter all the water from the sand, and that way we can measure how much sand we've got. Okay, so that's what we want to do. And the reason we need a wash bottle is because we need to make sure that all of the mixture gets into the filter paper and none is left in the test tubes down the bottom. That's why we need the wash bottle. And we have to ensure that we've weighed the filter paper. Before we do anything, we weigh the filter paper, and that's going to be M3. The reason why we've put it as M3 is because it's sort of not a hugely important measurement, as in it's not the key measurement. So we're going to just put it to the side just for now so that we can focus on the more important aspects of this experiment. We put them from the filter paper. Once we've got all the water filtered out, or as much as we can, we then transfer the filter paper to a pre-weighed evaporating basin. Remember that even though you have a filter, the sand does hold some water. The filter paper is not going to get rid of all of that water because it's just going to be locked in the sand. We have to get rid of that water. Otherwise, if we weigh the sand, we're going to have a bunch of sand and some water with the sand. And so the weight measurement will be the sand and some water. And that'll throw off our measurements. So we got to get rid of all the water by evaporating it. And so the pre-weighed evaporating basin has a mass of M2. Basically, M2 and M3 are just the weights of part of the apparatus that we're using. Not really the mixture, sand and salt and water. It's just the apparatus. So just keep that in mind. So then we rinse the tube, wash the sand that collects in the filter. That's what we do before evaporation. The reason why we wash the sand again is because when the sand is in the filter paper, the water contains salt. So if we evaporate the water, we know that salt doesn't evaporate with the water. The salt will be locked up in the sand, and then we have sand and salt after evaporation. And if we have sand and salt, when we weigh it, we're going to have a different measurement to what we would expect for just the sand. We got to get rid of all the salt, and we do that by washing it away. So when we pour water on the sand, the salt dissolves. The sand stays obviously the way it is because otherwise we'd have disappearing beaches. But so once the salt dissolves, it's free to move with the water. So the water will drag it away. So the water will drop down into the test tube, and that will bring the salt with it. If we've washed the sand thoroughly enough, we should just have sand and water because we'd have some water stuck there. So that's why we need to wash the sand again. Once we've done that, we remove the filter paper and place on a clean watch glass. So all that is just a little piece of glass. We put the filter paper there just so that nothing gets stuck on the evaporating basin or any of the other apparatus that we're using. And then we put the whole thing, the evaporating basin, the watch glass, the filter paper, all into an oven, a drying oven. So it's similar to your home oven, except we just don't turn it up as high. It'll be maybe 60 to 80 degrees in temperature. And all that does is just evaporate the water. Nothing really special about it, evaporates the water. And the reason why we say to a constant weight is because obviously if you're evaporating water, it doesn't all happen at once. Some of the water will disappear, then some more of the water over time. If you were to sort of plot, for instance, if this was your time axis and this was your weight axis, you'd sort of see that over time the weight would decrease, but after a certain period, it'd just flatten out. If it would be flat, that's your constant weight. The reason why we want a constant weight is because if we decide to stop here, there would be some water still in the sand, and that would throw off our measurement, obviously. If we're here, we know that all the water is gone, and so that's why we say a constant weight rather than dry. This is a quantitative way to say, look, it's really dry now. Finally, after we've dried it, we record the mass of the filter paper and the sand. Obviously, we can't get all the sand out of the filter paper, so we'll just weigh the filter paper and the sand. And that's our number M4. M1 was the mass of the mixture, M2 was the mass of the evaporating basin, and M3 was the mass of the filter paper. And here's the key one, M4 is the mass of the filter paper and just the sand. The way to evaporate things is there's a bit of a technique to it. So while I went through kind of the overview of how to evaporate, just put it in the oven basically, there is a bit of a technique to it, particularly if you want this experiment to be done, say, in the space of kind of an hour or so, which would be good for you to get the results in, say, one class. We partially evaporate the salt water on a hot plate. It's just like a stove top, it's just a piece of heating element, and we put the evaporating basin on there and just heat it. And this is to get the mass of the salt. In the case of the sand, we're trying to get rid of the water to get the sand measurement, and we've done that, that's M4. Now we want the mass of the salt. We've got our evaporating basin, which has the salt water in it, which is all of the runoff from the filter paper. So all of the water that we use to wash the sand has gone into the test tube. We put that water into an evaporating basin, and now we're gonna heat it so we can get how much salt we've got. So we heat it first on a hot plate to kind of get the water hot. We don't want it to be so hot that it's boiling because there's some issues associated with that I'll go through. After we get it kind of hot or warm, we put it in the oven as well, and that will get rid of all the rest of the water. To avoid the splattering of salt, so basically if you've ever boiled anything in your life, you'll see that drops of water go flying out when we put enough energy into it. We don't want to do that because if any water leaves, it could take salt with it. It almost certainly will take salt with it. So we want to avoid that, so we want to heat it kind of gently, and the way we do that is with this drying oven. You know, on a hot day, if you spill some water on the ground, it doesn't sizzle or boil, assuming it's not that hot. It kind of just gently disappears over time. Similar here, we went in the drying oven, we've got kind of hot environment, but it's not so hot that things will sizzle away, it'll just disappear on its own accord, similar to a hot day and you spilled water on the floor. With the hot plate, it's like if you pour water into a really hot pan, it's just gonna boil instantaneously and splatter and go everywhere. So this is just to get it high temperature without boiling, and then the drying oven is for just kind of to get rid of the water over time. Once we're done with getting rid of all the water, we measure basin, the evaporating basin that I just mentioned earlier, and the salt. We're not going to try and scrape away all the salt out of the basin, we're just going to measure it. And that's going to be M5. We can weigh the clean, dry sample tube. So the original tube where all of the mixture was in, we dry it out and then we weigh it, and that's going to be M6. So let's just recap on what all the weights are. M1 is the mass of the tube and the mixture. M2 was the mass of the evaporating basin, this one. M3 was the mass of the filter paper inside the filter funnel. M4 was the mass of the sand and the filter paper. And M5 is the mass of the salt and the basin, the evaporating basin. And then M6 is the mass of the test tube that we started with. So we had a test tube, we took all the stuff out, then we weigh the test tube. This is a table of it again. So mass of sample and test tube, mass of the evaporating basin, mass of the filter paper, mass of filter paper and sand, and mass of evaporating basin and salt, and then the original mass of the sample tube, so the tube that all the contents came in. Here are some sample measurements. So if we were to do this, this could be one of many sets of data that you could get out. How do we calculate how much sand and salt we have? We take the mass of the mixture. So how much mixture do we have? Well, that's easy. It's the total mass of the tube minus the mass of the test tube. Tube plus all of the mixture minus the weight of the tube gives you the weight of the mixture, and that's M1 minus M6. If you go back and look at the table again, that will tell you what each part is. And we'll call that M7, or we could just call it massive mixture. M7 is just easier to write, that's all. So the mass of the sand, remember what we measured. This is key. We have to think back to what we measured and what we want out. What we measured was the mass of the filter paper plus the mass of the sand. That was M4. We have weighed the mass of the filter paper previously. That's M3. So the mass of the sand is simple. It's just the mass of the filter paper plus the sand minus the mass of the filter paper. M4 minus M3 gives you a particular number based on the numbers that we got before. The mass of the salt, again, is easy. We've got the mass of the evaporating basin. We measured that. We've got the mass of the evaporating basin and the salt together. So you just take the mass of the evaporating basin away from that mass of the salt and basin, and you've got the mass of the salt. It's M5 minus M2. And finally, the mass of the water is fairly easy if you think about it. If we have the mass of the mixture that has water, salt, and sand, we've got the mass of the salt here and the mass of the sand here. If you just take them away from the total mixture mass, that will give you the mass of the water. And that's just a simple way, if you just think carefully through each measurement and each calculation, it's just simple additions and subtractions. Mostly subtractions in this case. The key part in this experiment is remembering, like, it seems convoluted. Why did we weigh the filter paper and then measured the filter paper and then weighed the evaporating basin, then weighed the evaporating basin and salt? The reason why we do all this, and the reason why scientists seem like they're doing really convoluted experiments, is because we want to reduce the error. Error is important. If we've got bad error, if we've got lots of error, then our results are essentially meaningless. If I tried to scrape all the sand out of the filter paper and then tried to scrape all the salt out of the evaporating basin and I tried to do all this fiddly stuff, one, that seems like a lot of work. Two, it's very hard to get all of it. It's almost impossible. How could we ensure that we cleaned out the bowl very well or cleaned out the filter paper perfectly? We can't. We have to kind of compensate for that by weighing a few more things and then just using our knowledge of mathematics to take them back and then get to the original result that we want. So that's why it seems like it's lots of extra steps, but those steps are important to reduce the error. The percentage by weight is just a fraction times 100%. If you went to the data, it would just be 1.467 grams over the total mixture mass times 100, and that's a percentage, and it's 20.7%. Same, you can do the exact same calculation for salt, just put the number for salt here, but the mixture mass stays the same, and you get 45%. So it's more salt than sand in this case, so there was probably more water than there was sand in our particular experiment. It may not be the same for you, but that's for this one. And for water, again, you can do exactly the same calculation. Just the mass of the water over the mass of the mixture times 100, and that's the percentage by weight of water in the mixture. There's lots of different percentage measures you could use. You could use percentage measure by mole, percentage measure by atom or something. You can use any measure that you want, but the reason why we say percentage by weight, even though it seems obvious, we want to ensure that everyone's on the same page. We want, say, a scientist in Germany or a scientist in Denmark to be able to replicate this experiment and get exactly the same number. So we have to tell them, what are we actually measuring? Are we measuring the weight, or are we measuring, say, the number of moles? That's why it's percentage by weight. It seems obvious, but just remember that there are lots of other ways to measure things in science. That's why we tell you this. And it's 3.8%. Accuracy is important. There are sort of three things that you have to be aware of. It's like ARV. Accuracy is one of them, reliability is the other, and validity is the last one. So accuracy can be improved in many ways. From what we've done, it seems pretty good. We've made sure to weigh lots of things, to not have to try and transfer substances from one place to another, and that helps. But some ways that we could improve it is to ensure that all the materials are quantitatively transferred from the sample tube to the filter paper and evaporating basin. So make sure the sample tube is really, really clean when we start weighing things. The other one is that we have to make sure that we wash the sand well. The sand can hold some salt. We want to make sure we get rid of all of that. So a lazy wash will give you bad results, but if you're thorough with the washing, you'll get generally really good results. For the salt, when we heated the salt water to try and get rid of all the water, don't let it splatter. Heat it gently and make sure that trying to vigorously flash boil it or something, you're just trying to gently get all the water out and have the sand just in the bowl. Another one is the drying of the samples. The mass will go down slowly as time goes on, but it will eventually stop changing. That's because there's no more water. So we have to ensure that we dry the mass to a constant weight. Sometimes if you aren't looking at it for long enough, it could seem like it's just not changing. It might just be, kind of fluctuating. Really, there might be the trend downwards. If we looked at it for a longer period of time, we would actually see that trend downwards. We're just too close to see that it's actually trending downwards. We just have to be aware of that. Always play it on the safe side. Leave it for a couple more hours if really necessary. If you're really suspicious about it, just be aware of that. Things don't just happen instantaneously all the time. So you just have to be aware that the filter paper is completely dry. And you have to be also kind of careful because you could use better materials. For instance, a filtering crucible might be better because filter paper is paper, and we know paper can absorb some water because it's a bit hygroscopic. It's made of mostly cellulose. All those OH functional groups on the sides can hold some water. Maybe a crucible is better simply because it's made of ceramics, and ceramics don't absorb water. Well, most of them don't. So that could be one way to improve the accuracy. That's one simple gravimetric analysis experiment, and hopefully you can understand how gravimetric analysis works and why it's important. It's pretty obvious why it's important because scientists weigh lots of things, and we always want to know compositions of things. It doesn't matter what it is. If we look at the mining industry, we want to know how much of a particular useful metal is in a rock. Or if we're looking at sort of like a steel making facility, we want to know how much steel we need to make or how much carbon we need to measure to make the steel. There are lots of industries that rely on measuring things, and those are just two of them. This is why this gravimetric stuff is really, really important. So hopefully you've understood how to approach a gravimetric analysis experiment, even a simple one like this. That will be important for your future understanding of more complex experiments that require lots of measurements.